Okay, so more Bayes. So today we are going to do our equation practice, like always, and then we're going to finish up on Bayes. Specifically, we're going to talk about MCMC again, because that part was fast and it's a difficult topic. And so I want to reiterate that I don't expect you all to be able to program your own MCMC chains. Okay, that's not what I'm expecting at all. What I do want is for you to have at least some conceptual understanding of what's happening here. Okay, just I view this very much like maximum likelihood in terms of the level of understanding that I would like you to have, right? So with maximum likelihood estimation, like I would hope that you would have like a general sense of what's going on in terms of, there's a likelihood function and you're trying to fit some parameters that maximize that likelihood. And there's like a bunch of details that go along with that, but most of the details are not super important for applied work. They are definitely more important if you're getting into more methodological work, but that's sort of the level of understanding I'm hoping we'll get to with MCMC. So it doesn't feel like it's just total magic, and it actually makes some sense conceptually in terms of what's going on. So we'll talk about that. It's basically just sort of finishing up our discussion of like introducing Bayesian estimation, and with a specific focus on MCMC. And then we'll jump into implementation with Bayes. Okay, so we'll be using the BRMS package to do that, and we'll actually start to fit some models. Okay, so we'll talk through that. Then we'll take a break, and then we're going to talk about logistic regression. I'm going to actually start that discussion sort of from the beginning. All right, and that is mostly because, at least in my experience, I didn't feel like I ever had a real great introduction to what logistic regression actually is. So, and like how it differs from standard regression. Okay, so I'm calling that logistic regression review. I hope it's a review. For many of you, it might not be a review though. Okay, but that's going to be, that whole logistic regression review part is really going to be just about like single level models. Okay, and then we'll talk about how we can take that as like our base model and just extend it into the multi-level form. Okay, and we're going to only talk about that through LME4 today, because I just didn't feel like we could get through all of it today. So next class, we will use BRMS for that sort of stuff as well. But really, as you'll see, I think once we implement with BRMS, it's really just a matter of switching out which library you're using to estimate these things, because the syntax is essentially identical. Okay. Okay. So any questions on that, or anything anybody wants to check in on before we get started today? Okay. All right, so on to the equation practice. So please launch R and get ready to go, R Studio. And then please read in the following data set. I only added this a couple days ago, so it's if you have the repo cloned, you'll need to pull or go ahead and go to Canvas, and you should see that data set there. It's just called 3lev.csv. And it looks like this. So we got school ID, student ID, the size of the school, the proportion of low-income students, the proportion of students who are mobile, and then some student-level variables, female, Black, Hispanic, whether or not they were retained, the year, and then a math score. Okay. So I didn't set a timer for you here, but I'll just give you like a minute or two. Okay. So moving on, let's fit this model. Okay, minute and a half, ready, go. Okay, so hopefully this one wasn't too terribly difficult. We have math as our outcome. We have mobility as our predictor, which is a school level predictor. And we have a random intercept at the school level. Okay, so then we have one bar school ID. Make sense? Any questions on that? Okay, let's try this one now. Okay, for this one, we now have year as a predictor in the model, which is varying at the within student level. Okay, so that's a level 1 predictor. And we have both the intercept and this year slope varying at the student ID level. So you see we have year, and the 1 is implied, right? 1 plus year bar SID. So that's saying we have both year and the intercept varying randomly by SID. And then we have female here as a predictor of the intercept. Okay, so female is entered there. That's a student level predictor. And then finally mobility, which is a school level predictor. And we're modeling, notice for our alpha, we have alpha j, k. So we have alpha varying randomly at the student level and the school level. So the 1 is implied here, and then we just have one school ID there. Questions? Okay, let's try this one now. Okay, so in this case, we have year as a predictor still. We have alpha jk, so that's the same as it was before. We have the intercept varying randomly at the student and school level, and the slope is varying at the student level, but not the school level. Okay, but then we have now Black and Hispanic, which are dummy codes, that are entered as predictors of the intercept, as well as female. But those predictors are also predictors of the slope minus female. Okay, so Black and Hispanic are also predictors of this slope, which is an interaction. Okay, so we have it like this: year times Black, year times Hispanic, and that's going to expand out to year plus Black plus Hispanic plus year colon Black, year colon Hispanic. Okay, so you could write it that way too if you wanted to. Then we just say plus female plus mobility. Okay, so that's this one and this one. So if we don't have an interaction, right, they're just predictors of the intercept. And then we have year SID and one school ID. Any questions on that? Okay, let's try this one. Okay, in this case, this part is basically the same, except now we have alpha jk and beta 1 jk. All right, so the year slope is varying at both the student ID level and the school level. Okay, at the student level, we have female as a predictor of the intercept and the slope. But notice the intercept predictor for female is also randomly varying at the school level. So whatever the effect of female is on their initial achievement, that's going to randomly vary across schools. Okay, so that also randomly varies at the school level. And then at the school level, we have mobility as a predictor of both the intercept and the slope, the year slope. And we have low income as a predictor of the intercept as well. Okay, so this is a fairly complicated model at this point. And so I would do it like this: year times female, that's going to give me this, this, and this. So this would be like year, female, year colon female, right? That's what this expands out to. Year mobility, so that would give me year, mobility, and mobility times year, mobility colon year, right? And then low income, that's going to give me this one. And then at the student ID random effect level, we just have year SID, just like we did before. And then at the school level, we have year, but we also have female randomly varying at the school ID level. Okay. Yep, Chris?
With the, we're using the same variable female, it looks like, for both the like level 1 and then also the random effect. It's not like an aggregated percent. Is it aggregating it to a percent, or is that actually
No,
like the dummy coded at level 3?
So this is the same variable here and here, right? That's just the interaction between them. So that's year colon female. And then it's this part right here, when we say female and school ID, we're saying that this effect is going to randomly vary across schools. Does that make sense? So we're not
The
doing
effect of what?
Say that again, sorry.
The effect of what? The effect
The
is
effect
varying
of female on their initial achievement. So it's when we specify things in the random effects like this, we're not actually saying anything about the variable. We're saying things about the parameters. Okay, so we're estimating the relation between female and their initial achievement here, right? That's what this is saying, because we have this year variable in there. So this is a predictor of their intercept. So their intercept is their initial achievement, right? So we're saying maybe students who are coded female score 2 points higher on average than other students, right? So that difference of 2 points, we're saying, is going to randomly vary across schools. So in some schools, it's only going to be 1.5 points. In other schools, it might be 3 points, right? It's that variance in that parameter for female that is randomly varying across schools. That's what this is saying.
Okay, thank you.
Mm-hmm. Good clarification. Any other questions? So if we were talking about a female level predictor as a school level, that would show up here, right? This or here. So mobility is a school level predictor. It only varies at the school level. Female varies at the student level. And so when we're specifying those random effects here, right, these are the ones that are varying randomly. And that's where we get this variance. So this is the mean structure of this random variation. And this is the variance covariance. Okay, let's fit this one now. You will probably run into convergence warnings. Don't worry if you do. And for all of these too, you can also just specify, like you can just write the equation and not worry about actually fitting the model too if you want. Okay, for this one, we have the intercept JK. So the intercept is randomly varying at the student and school levels. We have this year slope. It's randomly varying at the student and school levels. And then at the student level, we have female as a predictor of the intercept and the slope. Okay, so that's going to be an interaction. But both of these, the main effect for female on their initial achievement and the main effect and the effect of female on the slope, the year slope, are going to randomly vary across schools. So again, this is that same sort of thing where we're saying, students coded female maybe score on average 2 points higher than other students, but that 2 points is going to randomly vary across schools. So in some schools, maybe it's only 0.5 point. In other schools, maybe it's 4 points. And same thing for the slope. So we're saying maybe on average, students coded female, progress at 0.5 point less per year, right? But that's going to randomly vary across schools too. So in some schools, maybe females progress 1 point higher on average, and in other schools they progress 2 points lower on average. Okay, so those are both randomly varying across schools because we have the gamma 1k, right? But this is gamma 1 for the beta 1 and alpha. So those show up down here. And now the only other thing is we're estimating only the variances of these things and not the covariances. All right, so that ends up looking like this. Math, year times female, so that gets us year, female, right? Predictor of the slope. Mobility, that's here. Low income, that's here. And then we have year, SID, so that's this one and this one, right? And that gives us this. And then we have year times female, so this whole thing, year, female, year, colon, female, right? All three of those, plus the intercept, which is implied, are all going to randomly vary at the school level, but we use the double bar to say we're going to not estimate the covariances. Okay? That's a really complicated model too. Are there questions on that? Okay, I want to point out when we're doing these equation practices like this, I am trying to push you, right? So I'm trying to make it, I'm putting quite complicated models out there regularly to try to push you to understand these things better. Okay, so if you're not getting all of them, that's fine. And if you're not fully understanding the models, that's fine. But the intent is to help build fluency, and part of how we do that is to challenge you into more and more complex models. Okay? Yep.
Another question. Could you just explain what like the theoretical thought would be behind like estimating a variance covariance matrix for the student ID, but not the school ID? Like, what is that theory-wise saying?
Yeah, so this is tough because generally in this case, you would expect that the place that students start is going to relate to the rate at which they grow, right? That's not always the case, but you would generally expect that to be the case. So that's what this is saying. But what this would imply up here is that you're saying after you've accounted for that at the student level, then there's just not enough variance in that parameter left at the school level. So you can safely assume it's 0, even though in reality we know it's probably not 0 because none of these are actually 0, right? But you're going to just say, after accounting for it at the student level, there's not enough variance left to estimate that same effect again at the school level, right? So that would be for this one. And then for these, like this is just a stronger assumptions about your model. You're saying that the variance in that effect for female is not related to any of the other effects, and same with this one. But this is again where you would want to be careful about this for sort of two reasons. One is this model might be the best that you can do with your data, so you might just not be able to estimate all of those covariances without convergence warnings or failures. But you also, if you try to estimate all these things, you might be overfitting to your data. So you might end up with a model that doesn't fit as well because you're just estimating a ton of parameters here at this point, right? And so even though this is making stronger assumptions, it might be the best that you can do with your given data set. Does that help?
Okay. Yeah. And we would be looking at the IC values, not like the residuals, like the
Yes.
RMSE or anything like that. Okay, cool.
Correct.
Thank you.
Yes. Yep, Manuel.
Can you help me understand the interaction random effect year in female?
Yeah. So you're talking about this one randomly varying here, right?
Right.
So basically, this is just like it's just like this one, which is here, right? Except it's on the slope. So, we would say, let's say on average, kids gain 10 points per year, just to make it easy, right? And then this one is estimating the average difference for students coded female. So maybe on average, students coded female progress 2 points less than that, right? So students coded female progress on average 8 points per year, while other students progress 10 points per year. Okay, that's the average effect. It would be -2, right, for this one. And then here, when we're estimating this random effect, we're saying what's the variation in that -2 between schools. So in some schools, maybe the average female growth is 12 points. And in another school, maybe it's 6 points, right? So females in students coded females across schools probably grow at different rates, and you're estimating the variance in this average effect for female.
Got it. Thank you.
Yep. Other questions? Okay. I think we still have a couple more. We might not be able to get through all of these because we got a lot of stuff to get through. Let's just do at least a couple more. Let's do this one. Oops. Okay. I will be honest and say that this one I don't think makes a whole lot of theoretical sense. It's also missing a subscript, I just realized. So this is the only thing that's tricky about this, is that this is not alpha j here, it's gamma 1k. So this is the one that's randomly varying at the school level, not this one. Okay, so if you look at alpha j, it says alpha j, but no alpha k. All right, so I'm showing you this in part because I want to show you the syntax to create it. So that looks like this. Okay, and actually this, yes, no, this is wrong. So we have year, right, which is here. We have female, which is here, and then this is not correct. But what this, yeah, this is all messed up. What this is supposed to be is year SID. That's all right, but forget about this. This should be 0 plus female there. Okay, but so this part is how we say estimate a variance here without estimating the intercept variance. We put a 0 there instead of a 1. Okay, so that's just a quick, and you can do this. So we've used the double bar to constrain the off diagonals to be 0 or to fix them at 0. You can do the same sort of thing where you can estimate just one of them to be 0. So like you have an intercept and a slope, and you're going to fix that to be 0, but then estimate the rest of them by doing like 0 plus female school ID, and then you know, other variables, whatever other variables you have with school ID. So that's just another thing. Okay, let's do this last one, and then we'll move on. So we'll skip number 7. Manuel, you still have your hand raised. Okay, in this case, we have intercept varying at the student and school level, year randomly varying at the student and school level. So we have year, school ID, SID, and then we have female as a predictor of the intercept. So that's here, and then low income as a predictor, as a school level predictor of the intercept and the slope. So that's just year times low income. Okay, and again, that's the same as year plus low income plus year colon low income. Okay, so this part is the interaction that's, and you can kind of follow this back, right? This goes beta 1 here, which is not here, but it is here. So you can see low income is predicting this slope. Okay, so basically you would say in schools where they have, you know, 20% low income, we would expect this slope. And in schools where we have, on average, and in schools where it has 50% low income, we would expect this slope on average. Okay. All right. So that's it for the equation practice today. Any last questions on that before we move on? Okay, so let's switch to Bayes, finishing up on Bayes' intro. This part is kind of important. What we are doing is an intro, right? And so I'm trying my best to cover it fairly comprehensively, but it's a gigantic topic, right? It could and is a course on its own. So hopefully you're getting a general sense of what Bayes is, but just sort of realize there's a lot that we don't have time to cover. Okay. All right. So sort of revisiting what we did last time, just as a reminder, our posterior is defined like this, right? So we have a posterior, which is, we can think of as our updated beliefs, right? And that is created by the likelihood from the data times our prior information. Okay, so we have some prior beliefs, we collect some data, and we update our beliefs based on the evidence in the data. Okay, so if the evidence in the data is overwhelming, our prior beliefs sort of go out the window. But if the evidence in the data is sort of not very much, there's not a lot of information in that data, then it's going to be more of a compromise, and or we might just stick with our original prior, okay, depending on how much information is in the data. Okay, so if we just have a single parameter to estimate, like the mean, it's pretty trackable with grid search, right? We can just search a whole range of possible parameters and then compute the posterior, and it works. But even for simple linear regression, this becomes not really feasible, okay? Because instead of just having one thing that we're searching across, we now have three things. And so if you imagine trying to search across all the possible values for the intercept, all the possible values for the slope, for the slope coefficient, right? And all the possible values for your residual variation, that's a lot of things to search through at the same time. And you would be estimating the posterior for all of them and then doing all of this stuff to try to find the best combination, right? So this is essentially what it looks like, where it's now the probability of X, right? That's our likelihood given these things, these parameters, multiplied by the probability of those parameters. And then this part is the really nasty part where we are doing all these integrals, okay? So instead of doing that, which is really difficult, what we do is we basically just set up the posterior distribution and then we sample from it, okay? So this is similar to like thinking of like a theoretical distribution and then drawing samples from that. It's basically the same thing. We're just making that theoretical distribution to be relative to the parameters that we have in our model, okay? So it sounds a little bit like magic, and it feels like that too, for sure, when you're starting. So hopefully we're gonna take away a little bit of that magic feel here, okay? So there's a bunch of different ways that we can do this. They all use different forms of Markov chain Monte Carlo sampling. Okay, the one that we will be using is through Stan, and it's specifically called Metropolis Hastings algorithm. Okay, what I'm going to walk you through is actually just the Metropolis algorithm, which is a little bit simpler. Okay, but conceptually, we can think of this as the posterior distribution being like a hill. Okay, and let's just imagine that it's very dark and we are out in the wilderness and there's this giant hill and we want to have a good picture, we want to have a map, right, of what that hill actually looks like. And so it's very dark, so we can't see the hill, so we can't map it that way. So what do? One thing we could do is we could send somebody out to basically walk around that hill all over the place and record where they're at and record the elevation at where they're at specifically, okay? If they walk and walk and walk and they do this for a long, long time, then at the end, we would have all these samples basically from this hill that we can't actually see. We can't actually observe it, but we have a bunch of samples of what that hill is. Doesn't mean we're going to get the whole thing, right? That would take years, but we could get a good, if they walked around in a way that made sense, right, then we would get overall a good picture of the entire hill. Okay, that's basically what mcmc sampling is doing. We have this posterior distribution, which we can't directly estimate. And so instead, we're taking samples from it to try to get a good picture of what it actually looks like. Okay, so this is an example from this article that I just found the other day. It's linked here. It's a really good article. I would recommend, if you want to learn more about this, checking out that article. It has some R code in it as well. I'm going to actually walk you through the first part of the article example with the R code. I've modified the R code a little bit, but so hopefully this will make some sense. Okay, so if we think again about trying to estimate a mean with a known standard deviation, okay? So again, this is super simple, but this time rather than using grid search, we're going to use mcmc, okay? So let's assume it's a distribution that looks like this. We know it's normal, and we have some unknown mean, and then we have a known standard deviation, okay? So that distribution that we're estimating, we're saying what's the mean from a distribution that has a standard deviation of 15, okay? So we're going to start with some initial guess, all right? And hopefully this initial guess is guided by something, right? And it's not just totally random, but we'll say it's 110, okay? So this is the Metropolis algorithm, okay? First, we're going to generate a proposal distribution, okay? And the way that we do that is we start with where we're at and we randomly sample from around us, okay? And so I'm using a normal distribution in this case, but you could actually use other distributions as well, okay? And you could use any distribution. The point is you're starting somewhere and then you're going to randomly sample from around you in that space. Okay, so I'm saying start with a normal distribution with a mean equal to 110. That's my initial guess, right? And then sample with some standard deviation. It could be anything. It could be 1, it could be 10. And this is actually basically like a hyperparameter in the Mcmc algorithm. So basically, if you change this, it's going to, the algorithm will work better or worse. Okay, so if I made this bigger, it might make it better. If I made it bigger, it might also make it worse. And I don't really have a way of knowing that going into it. So I sort of just set it at something and then we can mess around with it. And there's no way to sort of estimate that directly, at least not with this algorithm. Okay, so I'm going to generate this proposal distribution, which is going to start with a mean at where I'm currently at, and we're going to randomly sample with some variation. So let's say I get a value of 108. Okay, so 110 is my initial starting point. I randomly sample and I get a value of 108. All right. Now let's say I look at my actual data. In this case, to make it super simple, we're going to say that I only have one data point. Okay. Normally we would have the likelihood of the entire data set, but rather than that, we're just going to say what's the likelihood of the data when we only have one data point, because that makes it very simple, right? So let's say our one data point is at 100. Well, obviously the mean of a sample that has one data point is just the data point, right? So that means our true mean is 100, right? Because our mean is just our data, okay? So we have one data point, it's 100, okay? What we're going to do now is we're going to compare the height of our proposal distribution, the one we just randomly sampled, from our current distribution, okay? So basically, we're going to say we have what's the likelihood of our data, 100, given a sample of 110 and a standard deviation of 15, versus, because this part's known, right? Versus the likelihood of our data with a mean of 108 and a standard deviation of 15. So we're basically calculating the likelihood of those two things. Okay? So in code, it's going to look like this. dnorm 110 with a mean of 100 and standard deviation of 15, and dnorm 108 with a mean of 100 and standard deviation of 15. Okay? And so you can see these two different likelihoods we get. The first is 0.021. The second is 0.023. Okay, so this one, 108, is more likely. Okay, what we're going to do now is we're going to compare these two things. If this one is our proposal distribution, right? If that one is higher in terms of our likelihood, which it is in this case, then we accept that. And that one becomes our new guess in our chain. Okay, if it's not higher, then we're going to randomly sample between the two. We're going to basically flip a coin to say which one we're going to accept, but it's going to be a weighted coin, okay? And it's weighted relative to these. So if one was, let's say, 0.8 and the other was 0.2, then you would 80% of the time select the first one, okay? So you're going to randomly select between the target and the proposal distribution, but you're going to randomly select based on their probabilities, okay? So if the proposal is accepted, that becomes the next sample in the chain. If it's not, then the next sample in the chain is just a copy of the current state, okay? That completes one iteration, and then you start over again by generating a new proposal distribution, and you go through that exact same process again, okay? That's one sample, and you do that over and over and over again, and that's how you walk around the hill, basically, okay? And this probability part makes it so that you're going to basically preference the higher points, okay? So you're going to have more samples around the top of the hill, right, than you are at the bottom. But you're randomly selecting from those so that you still get some samples from the bottom of the hill because you want a complete picture of the hill, right? But it's more important to have more samples at the top of the hill because that's sort of the most likely. All right?
Daniel?
Yep.
Could you explain how you got like a standard deviation of 15?
Yeah, so that's just, in this case, that's just what we set as our known.
Oh, okay. So why was it 10 and then 15 again?
Yeah, so the 10 is how we're randomly sampling from where we're at currently. Okay, so this part is we're saying the true distribution has a standard deviation of 15. But in our MC chain, each time we're saying this is where we're currently at, and now I need to somehow move somewhere, right? So I could set this at 1, I could set it at 5, I could set it at 0.1, I could set it at anything. It's just how I'm going to move from my current state to generate a proposal distribution.
Mm-hmm.
Does that make sense?
Yeah, thank you.
Yep. Okay, so that completes one iteration. So you're going to stop. There's no like convergence, right? There's no like, okay, now we are done. You just stop when you feel like you have a good enough picture of the thing that you're estimating. So that could be 100 samples, it could be 500 samples, it could be 50,000 samples, right? And the other thing is all of this that we just went through is one chain, okay? And very regularly, you're going to estimate the thing with multiple chains, okay? And that's because you might want to start one chain at 110, like we did, start another chain at 90, start another chain at 85, and start another chain at 100, right? And then let all of them kind of run, and then you can kind of collapse the information across the chains, okay? So if we want to actually do this in our code, it would look like this, okay? I'm going to first set a seed to make it reproducible. So when I say set.seed, that's just going to make the random number generation be the same, okay? So it's the random number generation is going to start at the same place each time. So then when I say R norm or whatever, I'll get the same results. All right. So this is just for reproducibility. Then I'm going to create a vector for my samples. Okay. So I'm going to say 110 as the first part of that. And then I'm just going to repeat NA, so just missing data, for the rest of it. And I'm saying we're going to do 5,000 samples. Okay. So rep NA 4,999 times, and then the first sample is 110. Okay. Then we're going to loop through this, and I know looping is complicated, so if you don't totally follow what's going on here, that's okay. But basically, I will walk through this, and hopefully it'll make at least some sense. Okay. So you're going to say for I in 2 to 5,000. So that means we're going to do this, everything that's in here, this whole part, we're going to do this where I, which you'll see is like here and here, right? And down here, everywhere where I is, it will swap out for 2, and then it'll run it all again, and it'll swap out for 3, and then 4, and then 5, and then 6, okay? So this I ends up just being each of these numbers as it runs through iteratively, okay? So the first thing we're going to do is generate our proposal distribution. Okay, so I'm going to say R norm, randomly sample from a normal distribution one time, get one sample, where the mean is equal to the samples I minus 1. Okay, so for the first time, that's going to be 2 minus 1, which is going to be samples 1, which is going to be 110, right? So my first mean is going to be 110. And then a standard deviation of 10, again, we could set this to whatever we want. This is how we're going to take a step in whatever direction for our proposal distribution. Okay, then we're going to calculate the current and proposal distribution likelihood. So I'm going to say, give me the likelihood of the current state, which is going to be d norm I minus 1 with a mean of 100, which is our observed data point, and a standard deviation of 15, which is our known standard deviation. Okay, so that's for our current. And then for the proposal, it's just going to be d norm of proposal, this thing we did right here, with the same parameters. Okay, then we compute the probability ratio. So we take the proposal and divide it by the current. So if the proposal is higher, this is going to be greater than 1, right? Otherwise, it's going to be somewhere between 0 and 1. So what we do is we say, give me one draw from a random uniform distribution between 0 and 1. And if that probability ratio is greater than that, which it's always going to be if the proposal distribution is greater than 1, right? Then accept that proposal distribution. Otherwise, give me the current one as the next one. Okay, so we're going to reject, it's just the current. Okay, so this is a way to randomly select between the two when the proposal is less than the current, okay, in a way that the probabilities are weighted. Okay, so we can do that 5,000 times, and then we end up with something that looks like this. Okay, so this is the iteration history. So we have, I'm saying iterations 1 to 5,000, and then the value is that samples thing that I just created. We put the iterations on the x-axis, and then the value on the y-axis, okay? And then I have a y-intercept at 100, which is our true value, and you can see it's pretty much right there in the middle of those things, okay? We can also look at the density of it, and it's going to look like this. So the vertical line now represents our value of 100, and you can see those samples do center right there on 100. Okay, so that's the basic process. Of course, when we're doing it with Bayes, then the way that we calculate these likelihoods and things are different. And we're also using a slightly more complicated version of this to account for a few other things. But this is the basic idea of it, is that we're just going to calculate these likelihoods based on these parameters. Okay, so we're going to randomly start the parameters somewhere and then look at the likelihood of the data with those parameters, and then look at the priors that we have set up, and we're going to combine them all and essentially randomly select from here, from the posterior, over and over and over and over again, and select, move around that hill in a way that is the probability is related to the posterior likelihood. Okay, so that's the basic idea, and I know it's probably still like confusing, and that's okay, because again, as I mentioned before, my hope is that you just have a sort of general sense of what is going on here. Okay, if like specifically that random sampling part doesn't make sense to you, that's okay. But I hope that you have a general idea of, okay, we're setting up these parameters, we're starting them at random spots, and then we're going to try to look at our posterior distribution and jump around those parameters to get samples from our posterior distribution in a way that is equal to sort of the probability of it. Okay, that makes sense? All right, I want to share one other part real quick here, which is this is uploaded to Canvas as well, but you will see there's this scripts folder, okay, and there's this Bayes update plotting. Okay, so I mentioned last time that I would get you a script that you could play with the priors and play with the data and things and try, and then from there, hopefully you could start to understand how priors and likelihood sort of work together. Okay, so that's what this script is, the one that says Bayes update plotting. So what you'll need to do to run this script. And this script is like not the best. If I were to like try to put this in a package, I would write this code slightly differently, but I just wrote it fast. So it should work for you, but if you run into problems, let me know. But what you're going to do is just load the tidyverse, and then this is a function. So if just on line 4 here, you just run that. Same thing here for plot update. You should just be able to run that. And then down here is where you're going to actually start working with it. Okay, so you can set some true data. So let's say I want to do 20 data points instead of 50. I want to set my mean at 2 and my standard deviation at 5. Okay, so that's my true data. And then, oh, except I have to keep the standard deviation the same because we're only doing the mean. We're only searching for the mean. Okay, so but we'll set it at the mean at 2. Okay, and then we're going to search a grid. So you can change this grid that you're searching for too, but this is just the possible mean values you're going to search through. So from -3 to 12, but in increments of 0.1, and you could change the increments to. And then you're gonna just do this. So this is this Bayes update, okay? And you're going to give it your true data, and then I think these are what are those? Let me go back up here. Bayes update, true data, prior mean, and your prior standard deviation. Okay, so let's say I want to have a prior mean of. So let me actually put this here. Prior mean equals 1. Prior SD is equal to, well, the prior standard deviation, no, prior standard deviation can be whatever, it doesn't matter. Let's set that to 5, okay? And then we're gonna have the grid that we're gonna search through. This plot update, what it's gonna do is it takes these values, which are which samples do you wanna show. So before I get to that, let's just run this Bayes update here. And you'll see I get this data frame in return. So here's data points observed. So at this point, I've only observed 1 data point, right? Here's all my possible means. Here's my prior likelihood, my data likelihood, and then the posterior likelihood, okay? And so if I say plot update 1 to 6, and then I'm going to add a vertical line on the true mean. So in this case, what did I set it at? The true mean is 2. So I'll put an x-intercept at 2. Okay. Then it's going to create plots that look like this. Let me switch my share here. So it looks like this, right? So here's this black line is the true mean. This blue line is my prior. And then the green curve represents my posterior distribution, and the sort of reddish line represents my data likelihood. Okay, so this is with 1 data point observed. After 2 data points observed, notice the posterior likelihood is increasing. 3 data points observed, 4, 5, 6. Okay, and we have total, we have, shoot, hang on. Okay, total we have 20 data points that we created. So let's run this again, but let's look at, say, the 16th to the 20th data points, okay? And then you can see it looks like this. So now the posterior likelihood is getting really, really high. And by this point, the peak of that posterior distribution, I know that that's small, but the peak of that posterior distribution is very close to the true mean. Okay, that makes sense. And then the other thing is you can do, so now I'll try again with, in this case, this is just an example where I'm saying now I have 500 data points, setting the mean 50, right? And then I can do that again. This is for the 1st to the 9th data points, whatever, okay? And then the last thing, this is just kind of fun, but there's this animate update. So you can run this, and then you can do the same thing, but all you have to do is Bayes update, put your parameters, and then animate update. And what it will end up doing is animating the process going from 1 data point, 2 data points, 3 data points. It takes a second, so just be a little patient here. And there it is, except we can't really see it. Okay, so you can see the prior never changes. The likelihood of the data points do, but you can see how the posterior shifts as more and more data are collected. Okay, so you can play with that script. You can change the means, the priors, etc. Hopefully that will give you a better idea of how these things sort of work together. All right. There's also in there is, I mentioned before, but there's another script that walks through mcmc sampling with linear regression with Bayes. So you can look at that also and ask me questions if you want. It's called MH. I don't actually think, upon reflection though, it is actually the Metropolis Hastings. I think it's still just the Metropolis, but anyway. So Bayes update plotting and MH script. Okay, those are the two that you can look at for more of this. Questions on that? Okay, so if you want to play with that, obviously you don't have to, but please feel free to, and then let me know if you have questions as you are playing around with it. Okay, the good news is we don't have to write our own mcmc chains, right? We have Stan to do that for us. Stan is the backend that is used by this package that we will use called BRMS. Stan is a really powerful, by far the most powerful software currently for Bayesian estimation. It can fit any model you can think of because it's a programming language, but it's only for Bayesian inference. Okay, so you can, what BRMS does is it allows you to write formulas in R and then estimate them with Stan. So the syntax that we write in R is essentially equivalent to LME4, but it's a lot more powerful than LME4 also because we're using Bayes and we can do all sorts of additional things. Okay, we can do missing imputation data on the fly, which is really nice. We can impute from the posterior distribution. We can estimate multivariate models, so you can actually estimate like even structural equation type models with BRMS. You can estimate things like multi-membership models, which I will actually probably talk about a little bit next time, if not this time. I got that in the slides now, Brock. But you don't actually have to have that either. But BRMS is a super nice package, okay? We're gonna mostly do it to replicate stuff we've done with LME4 at this point, okay? So what is it? BRMS stands for Bayesian Regression Modeling with Stan. Okay, so I kind of mentioned what Stan is already. Here's a link to Stan. This is, like I said, it's its own process entirely. It uses the most sort of advanced mcmc sampling that's out there currently, and it's a lot faster than most other previous Bayesian estimation algorithms or whatever out there too. But as I'll talk about more in a bit, it's still going to be way slower, way slower than maximum likelihood. All right, and that's just sort of one of the downsides of using Bayes. So syntax is similar to LME4. Specification of priors is pretty easy, but you don't actually have to specify them at all. If you want to just use the default priors, they're flat, and so that gives you more like basically the LME4 type of results. And there's a whole bunch of things that you can do after fitting the model, which we'll talk through some of them to sort of inspect your model results. Okay, so let's go ahead and do this. Hopefully you have BRMS installed. I asked you to through one of the announcements, but if not, go ahead, just run install.packages BRMS, and then we're going to load it, and we're going to start out with the sleep study package. Okay, so, or data set. So sleep study comes from LME4. So do LME4 : sleep study, that'll get you that data set. And we're going to start out with just a simple linear regression model. Okay, so BRMS, all we do is say BRM, reaction is our outcome. That's predicted by days. Okay, I'm going to keep talking while you go ahead and do that. But what's going to happen when you do this is it's going to first give you a message that says compiling Stan program, I think, or something like that. Okay, and that's because Stan is written in C. Okay, that's part of what makes it really fast. C is a very low-level programming language, so it's very fast, but it's harder to write. Okay, and so but C also needs to compile, so it needs to basically, you write instructions, it looks at those instructions, it compiles it, and then it does it all at once, basically, essentially. Okay, so that's that can sometimes be the longest part, but not often, because usually sampling will take a while. Okay, by default, it's going to run 4 chains, and it's going to run them sequentially. So it'll start with first chain, takes 1,000 samples from it. Okay, then it goes to the second chain, takes 1,000 samples from it, third, fourth. I don't know why I'm getting this weird output. That's not what yours will probably look like. It should say sampling from chain 1, and then it'll give you updates, and then sampling from chain 2, and it'll give you updates. Good. Okay, so I'll give you just a little bit more time to do that.
Has anybody ran this and gotten a big error?
What is the error that you're getting?
Pragma diagnostic pop could not pop, not matching push, and first error generation, blah, blah, blah. Is that what you're getting to? I'm seeing a nod. Oh, different errors.
Yeah, I don't know. So if you're running into issues with BRMS, you should probably go here. Oops, that's not what I wanted. BRMS. Okay, here, I'll put it in the chat. But this should, well, yeah, I don't know. This should just work. But I'll put this here because there's a lot of documentation for it. Yeah, well, so the command standard part is actually not even required. It's just for additional speed that I will mention here in a minute. But the BRMS part, it should just be, you know, this. So, yeah, I'm not sure why you would be getting additional errors. Let's see. So yeah, I think I'm going to probably just move on for now, and then maybe we can, if you're still having errors, we can talk about it more later and see if we can figure out what's going on. It might be something to do with C and a C compiler. So that's my guess. Okay, after you've fit the model, though, you should just be able to call summary on that model, okay? And it will look like this, okay? So we have some information up here about the actual model. It tells you the data. Don't worry about this stuff for now. It says we used 4 chains, each with 2,000 iterations, but you also have 1,000 that are what they're calling warm-up, okay? Generally, this is actually called burn-in. But I think the warm-up is slightly different, but either way, those 1,000, those first 1,000 just get discarded, okay? And this is because the way the Mcmc sampling works, we're starting out at random spots, right? And then so our first guesses are probably going to be pretty far off. And then it's going to jump around until it gets to a stable point where now it's looking around the likelihood and we're pretty confident that we're in the right general space. So we want to just discard those first, in this case, 1,000, but however many you want to set. Okay. Thin, we're probably not going to worry about thin too much, but what that means is the default is 1. That means give me all the samples. If you said set thin to 5, it would take only every 5th sample. Okay. And the reason that you do that, or 10, it would take every 10th sample, right? The reason that you would want to do that is because the chains get correlated, and so sometimes that can end up with bad parameter estimates as well. So by thinning, you're taking only every 5th or 10th or whatever iteration in your chain, and that can help decorrelate the chains, which makes them more stable. But this is something that used to be very common in sort of old search algorithms and is less so now with the more modern methods that Stan uses. So most of the time you'll keep thin at 1, but sometimes you might need to adjust that as well. So it says there's 4,000 total post warm-up samples. So that's what we're going to use for inference. When we're looking down here, the first thing that we'll want to look at is this R hat value, okay? And this is a measure of between chain mixing. So basically, you have 4 chains. Are those 4 chains sort of all converging to the same basic solution, or are they kind of in totally different spots? All right. And so R hat should be 1.0, okay, as it is here. If you see 1.00, you're golden. If you see 1.01, you're still fine. If you get above like 1.1-ish, then you're going to start to worry because your chains are not mixing well. Okay, they're not really converging to the same basic solution. So there's other things you can do about that, etc. But this estimate now is by default, I believe, is the mean of your posterior distribution. Okay, and then you have lower and upper bounds of that distribution using 95% range by default. So this is a 95% credible interval, not confidence interval, right? And then same here for days, all right? So this is basically just like LME, well, not LME4, this would be like LM, actually. Okay, and then you have sigma down here, which is your residual variance, and you will want to look at the R hat value for that one as well, and it is 1.00, so you're good there, okay? R hat, though, just means that your chains are converging to the same solution. It doesn't mean it's correct, right? And so part of the way that we look to see if things are correct, well, I guess I'm not quite there yet. We can look at what our relation looks like. So you can use this function conditional effects, and it'll just plot the fixed effect for you. If you have multiple, it'll just say next, 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 okay? So conditional effects, this is our relation between days and reaction time. Okay, so reaction time goes up on average as days increase. This is days without sleep, so makes sense. But of course, we're fitting the wrong model, right? We're fitting just a simple linear regression model when we're using data that are illustrative data from LME4. So we know they're multi-level. Okay, so this is the model we should actually be fitting, where we have a different intercept and a different slope for every participant. Okay, so we do that by just extending the model just like LME4. Okay, we could say 1 plus days here if we wanted, but we have reaction is predicted by days, and days plus the intercept is going to randomly vary across subjects. Okay, and you can try to fit this one if you want as well. It'll take a few minutes, probably maybe a minute to fit. But then as you do this, notice you have these R hat values again. That's the first thing I would look at. And then you have your fixed effects, right? But they're not really fixed because they're distributions. But 251 is your average starting point, basically, right? And this is the average of that posterior distribution, 10.45 for days. So reaction time is going up on average 10.545 points per day. But then you have the uncertainty around this. But then up here, you also have the standard deviation of the intercept and the standard deviation of days. So this is equivalent to our random effects before, okay? And we also have the correlation among them. So this is that variance covariance matrix part, and we're just estimating the actual standard deviation here, okay? Notice we get the lower and upper bounds of this thing for free, right? It's part of the estimation because we have a posterior distribution. So we're always getting uncertainty in every single effect that we estimate. Everything that we estimate, we're not just getting a single answer, we're getting a distribution which we can summarize however we want. Okay, so I've mentioned with LME4, right, if I'm presenting the results, I would always present my random effects, my random effect estimates with confidence intervals. But sometimes estimating those confidence intervals can take 4 times as long as it takes to fit the model, which is not a big deal if your model is taking 30 seconds to estimate, but it is a pretty big deal if your model is already taking like 3 hours to estimate, right? So in this case, it already comes with that uncertainty built in, okay? All right, we can look at the fixed effect again, fixed effect. And you can see the uncertainty is increased. That's what we would expect because we have now accounted for this between subject variation. So basically, before we were overconfident in that effect, whereas now we're accounting for this better. Okay, so I mentioned back here that R hat at 1.0 is a good thing to look at. That's making sure your chains are all sort of mixing and coming to the same general solution. But that doesn't mean that your model is doing the right thing. So one way that you can check that your model is approximating your data is you can do things like this. Okay, so here I'm looking at I call PP check, so posterior predictive check. All right, and what we're doing is we're looking at the density of our outcome in this case. All right, and we are comparing that against posterior predictions from our model. All right, so basically what I'm going to do is I'm going to go into my posterior and I'm going to take one combination of my parameters, okay, and I'm going to make the predictions for it. Then I'm going to go in and do it again, get a different sample that's going to be different combinations of those parameters, and I'm going to make predictions. Okay, so each time I do this, I'm getting a new prediction for my outcome based on different combinations of my parameters, which are coming from my posterior distribution. Okay, so this ends up looking like this. It's sort of on the slides, it's a little bit hard to see, but you can see I have this nice blue line, right? That is my observed data. That's the density of my observed data. Okay, and then this Y rep is repeated samples from my posterior distribution. And so you can see each line is different, right? None of them are the same, but overall they're giving a pretty similar shape to my observed density. So that's good. That's a good indication that my model is actually capturing the same sort of overall shape as my outcome. Okay, which is good. That doesn't mean everything is solved still. It doesn't guarantee me anything, but specifically, I want to make sure that I would want to make sure that this is approximating that and that it's not like wildly different. Okay, because that would mean I have probably some assumptions in my model that are not in reality. Okay, and I'll show you an example of that in a little bit. But questions on this? Okay, you can do more checks, and I know this goes off the slides. For some reason, I couldn't get the plot to squish down. But if you just call plot on whatever model you fit, you'll get something that looks like this. Okay, so this is the density of each of the main effects that you have in your model. So these are all the things I'm estimating. And then these are the chains. Okay, so you can see 1, 2, 3, 4. This is just like I showed before, where we have the iteration, like the chain iteration here on the x-axis, and then its value on the y-axis. So on your actual local, when you look at this, you'll be able to spread this out and make it more visible. Okay, and I think these are the fixed effects down here. Okay, and specifically, I should mention what you should be looking for here. These ones are just kind of the density, but these ones over here specifically, you want to make sure that you're seeing that same mixing of the chains. My cats are going crazy in the background. You want to see that you're seeing that mixing of the chains, right? So one chain isn't way up here and another one's down here. Like they should all be kind of mushed together, and it should look kind of like random noise through here. Okay. All right. Even more, I'm not going to do this, but you should do this if you had fit the model. Use launch shiny scan, and that'll get you a shiny interface where you can click through and look at different parameters and look at the chains and look at the density and look at the posterior predictive checks and all sorts of stuff like that. So, but basically, it gives you a graphic user interface to do the same sort of checks that we just looked at, and even more. And what's nice about that too is you can actually click buttons to just save. I think you can save the code to reproduce those things, but you can definitely just actually download the plots from there if you wanted to present them in a paper or something. Okay, so that's like basically it. I mean, that's BRMS in a nutshell, and very, very quick. But when we're actually fitting models, right, we're going to probably want to do some model comparison. That is my general approach to fitting models. Start with a theory and then have competing models basically that go with that theory, right? And then sometimes from there, you're going to have to make compromises just because of the data that you have, and you're not going to be able to estimate everything that you theoretically think is important. And so then you have to make model parsimony decisions. But when I'm fitting models, like I'm always doing it from this model comparison sort of perspective, okay? When you want to do model comparison with Bayes models, there are two primary ways that you would do this. This one, the widely applicable information criteria, it also has some other name. I can't remember it off the top of my head. I think it's like Watanabe and somebody else information criterion. Anyway, this one is just like AIC or BIC. Okay, it's interpreted the same sort of way. You look at differences in the values between them, and you're good to go. All right. This one is called LU, leave one out, cross-validation. And this is not estimated actually through cross-validation, but it approximates the same thing that you would get if you used cross-validation. Okay, and so what that means is, let's say you have a data set, right? And you remove one singular data point, okay? You fit the model to the rest of the data, and then you would have some parameters that you estimate. You use those parameters to predict that one left out data point, okay? And you see how far off you are. Then you do it for the next data point, and then the next data point, and then the next data point, okay? So you would fit the model. If you have 200 data points, you would fit it 200 times, each time leaving one different data point out, and then using the model parameters from the rest of the 199 to predict that one left out data point and see how far off you are. Okay, so both of these are estimates of the out of sample predictive accuracy. So how accurate would your model be on average for left out data? Okay, LU is similar to k-fold cross-validation if you're familiar with that, but with only having one singular data point. And then WAIC is similar to AIC and BIC, as I mentioned. Both can be computed with BRMS, and LU is approximated, not actually estimated, so it doesn't take a bunch of time. Okay. The way we do this is we just call LU on the model, okay, and then it estimates it like this. And these values by themselves are not really interpretable. okay? Also, this is a pretty complicated topic overall. This paper here that is linked is probably the best that I have seen out there. So if you want more information, go there. As I mentioned, we have to kind of skim some of this stuff because we just don't have enough time for all of it. But that's how we get the LU for one model. And here it is for M1. And in this case, we're saying, okay, 3 observations, we get this like warning for. And so that's a little bit concerning. So we could add this in if we wanted to. But you can look down here and you can see 172 of them were good, 5 were okay, 1 was bad, and 2 were very bad. Okay, this is still going to give us a basic estimate of this. So now we have this value -861 as compared to -953. Okay, so that is telling us that this model is fitting better because it has the higher value. Okay, we can do a similar sort of thing where I say plot LU sleep 1 M1 and label points true. So now it has this line at 0.5 and then at 0.7. Okay, above 0.7 is pretty problematic. So that's 0.8. So we could look at our data at line 8 and see what's going on there. And then this one, 57 and 60, those ones are the highly problematic ones. They're above 1. So we could look at those as well. Okay. So large values are an indication of model misspecification. Okay, so those values are so far off that there's probably something that we've misspecified in our model. Okay, that's the basic idea of looking at that. The problem is, unfortunately, smaller values don't guarantee a well-specified model either. Okay. We can also compare these. So we do LU compare and compute the LU on each of those. And we get this value, which we're going to interpret relative to the standard error. Okay, so we have -92, which is, you know, almost 4 times as big as the standard error. So this is saying that's pretty good evidence that M1 is the preferred model, right? The one up here. Okay. WAIC is going to be basically the same thing. We can compare with that one as well. It tends to be a little more finicky, so notice it's saying we recommend trying LU instead. All right, very quickly here, and then we will take a break and move on from this for now. Here's an example where I'm fitting a model to this kidney data, okay? And I'm starting out by just fitting a linear model just like we normally did. Here, when I'm doing the PP check, I'm using ECDF overlay rather than that density. But specifically, I'm doing that because you can see why, right? Our observed data, we have 0 cases that are below 0, right? Nothing that is observed goes below 0. And then it increases from there. When we're using a linear model like this, we have a bunch of predictions that are where our probability is, you know, up here when it's below 0. So that's an indication, and then it's way low here, right? So it's way too high here because it should be 0, and it's way too low here, and then probably goes high again here. So this is not really matching our overall trend like we would expect it to. So this is an indication of model misspecification. So we could try fixing this by changing the distribution, okay? Because our model is not normally distributed, all right? So we could plot the raw data, and it looks like this. So we might think, okay, well, let's try something different then. Maybe we try a Poisson distribution. And I realize we haven't talked about these type of models yet. That's okay. Well, nope, that's not working either. Not at all. All right. So this is, again, normal distribution doesn't work. Poisson distribution doesn't work. What does, right? We need to find a distribution that's matching our data. And so in this case, it's going to be a gamma distribution is going to be the best match. And so you can see now that's working really well. Okay. We're going to go to break here in just a second, but when we come back, we're going to talk about alternative distributions. We're going to mostly talk about the binomial distribution, but I'll show you a little graph that talks about other distributions as well. Okay, but that's how that PP check is used, is to see that our model predictions are matching our observed data, basically, right? They're following in a similar sort of trend. And I also want to mention that this PP check takes a whole bunch of different arguments. Okay, so by default, it's going to do the density, as we saw in the first time. But this is an example where we're doing ECDF, which stands for the empirical cumulative distribution function, right? But then there's a whole bunch of others too. And what you can do is when you say type, you can say type equals anything that doesn't actually exist. So type equals ABC, and it will list all the possible types for you that you can look at. Okay. All right. Let's go ahead and just pause there. I'll come back to this when we're done, but let's go to break. That's a lot of stuff. So, okay, let's take a 5-minute break. Okay, let's get started again. So I want to just at least talk about specifying priors real quick, okay? And then I'll kind of skip over the rest of this because we've got to get to the binomial stuff. So if we want to specify priors, there's quite a few different ways that we can do it. And I think we have some other examples later on how to do this. But I just want to mention, so here we say prior, we're going to put a prior with a normal distribution mean of 0 and a standard deviation of 0.5. And then I specify class equals B. Okay, so I'm specifying this same normal distribution prior for all of the betas, right? So basically for age and sex, okay? So this seems like a pretty tight prior, right? A mean of 0 and a standard deviation of 0.5. So ideally, this would help shrink the parameters towards 0, much like a ridge regression type of thing, okay? So this is like a penalized regression, essentially. We can fit this model, but then when I fit this model, notice I also have this thing, sample prior equals only. So in this case, when I'm fitting this model, what I'm doing is actually ignoring the data altogether. And I'm only sampling from my prior, okay? And I can do this because that will give me an idea of how my priors are sort of working, okay? So in this case, you can see the fixed effects both end up right around 0. But if I make predictions from this model, they explode off into space, right? Look at how huge some of these predictions are. Like this one's like, we have one for female that is like 100 billion, right? And so that doesn't make a lot of sense because we're thinking about, thank you, because we thought we specified these priors pretty tight, right? Mean of 0, standard deviation 0.5. So why does that happen? Well, in this case, it's because we have this log link. Okay, so when I fit that model, I said gamma distribution with a log link, and we'll talk more about what links mean here in just a second. But age is coded in years. Okay, so imagine we had a coefficient of 1, which is only 2 standard deviations above what our prior would say, right? So I mean that's a fairly extreme, but it's not like unbelievably extreme. And so if we had a coefficient of 1, well, because age is coded in years, that's going to be 25 times that. So the exponentiated version of that, which is going to be this gigantic number. I don't know why it's showing up like that, but that's like 7.2 times 10 to the 10. 7.2 with 10 zeros, right? 72 with 9 zeros, rather. So that's why it's because of this log link. Okay, so basically the take-home message on this is that specifying priors is hard, right? if you're using anything other than an identity link, which is what we use for normal Gaussian linear regression models, then you're going to end up with priors in many cases. You're going to end up with a prior that you think is maybe pretty tight, and it ends up being very diffuse. Okay, so it's very not informative and not actually doing what you think it is because of the scale of the predictor, and then potentially because of the link that you have. Okay, so it's hard. Everybody struggles with it, so don't worry if you're struggling with it as well. And be particularly careful if you have anything other than an identity link. So if you're in this world of generalized linear models, so you're modeling anything other than a continuous outcome, then you're going to have to be particularly careful. Okay. Just real quick, here's a model we fit with LME4. This is that popular data extroversion with the extroversion slope, right? When we do that, we get these results: 2.47, 0.49, 1.73, 0.16, and negative 0.95. We can compare that to the LME4 model, and we see we get essentially equivalent results all the way across the board. Okay, so that's showing you that when you have diffuse priors, you're going to get the same results that you get with LME4. The nice part is that you can include additional information if you want, but now with that posterior, you can do a lot of other things as well. Okay. One last thing on priors. Often, I think just going with diffuse priors is going to be okay. But if you want to specify additional priors on things like the variance components, this is part of what makes Bayes hard also, I think, is that you have to learn about all these other distributions that exist, okay? Because different distributions besides just a normal distribution is going to help you specify priors in a way that is going to make the model actually work. So with the standard deviation and other random effects, you use this, I think it's pronounced Cauchy distribution. And so this is like a half Cauchy distribution where it's everything less than 0 is nothing. There's no probability density, but above that, you have different values of that. So this is 3 different values. That's probably the most common for that. So here's another way of specifying priors. This time I'm doing on the normal, or for class equals B. So this is for like the fixed effects. And then for the standard deviations, I'm saying use a Cauchy distribution with a sigma of 1. Okay, so that would be like this green one. So we're saying it's most likely that the standard deviation is going to be low, right? And then increasingly large standard deviations are increasingly less likely. Okay, so then we would specify it like this. Here I've specified the priors outside of that, and then prior equals priors. In this case, it's almost no difference because there's a fair amount of data. All right, this is about speed. I sort of mentioned this before, but Bayes will always be slower than LME4. There's just no way to make that not the case. You can use this command stand backend if you want, which will speed it up. So you can use this code to install it. And then from there, you can install command stand with command stand R, this package, install command stand. And what that's going to do is it's going to basically use R to call the command line. So it's going to use like terminal. And then it's going to fit the model from there, which ends up being faster, even though it sounds like extra steps. So here's 3 different models. This is just the standard sequential model. This is the same model, but with the command stand R backend. And then this is the same model, but with command stand R backend and cores equal to 4. Okay, so parallelizing it is another thing you can do. When I do this, I get each one is progressively less. So 112 seconds, 84 seconds, and 42 seconds. Okay, parallelization is good and will often result in performance gains. It's also not always going to be as much of a gain as you might expect. Okay, so just be careful about that. All right. I'm going to just skip past this. There's advantages, lots of advantages to Bayes, I think. The main disadvantage is that it's slower. And you might run into pushback from people who don't understand Bayes, basically. Okay, take a deep breath here. Now we're moving on to logistic regression. Okay? Questions on anything before we move in? Okay. Okay, data generating distribution. Up to this point, we have been assuming that the data were always generated by a normal distribution, right? So if we think about simple linear regression, again, we could write it like this, right? Where we say like wages, our wages data, are generated from a normal distribution with some mean structure and some variance. And the mean structure is defined by this linear model. So we're basically embedding this linear model as a replacement for that mean term in the normal distribution. Okay, let's go ahead and copy this code and then walk through this with me. Okay, so this is the wages data, and we could fit this model that we have here by saying hourly wage is our outcome. That's predicted by experience, okay, and the data is wages. I'm going to move on, but you just keep doing that until you have it done. Graphically, this model is going to look like this, okay? So we have experience on the x-axis and hourly wage on the y-axis. Now, when we've played with these data before, we looked at the natural log of wages, LNW. Okay, and when you look at the data like this, it makes more sense why we would use the natural log of wages, because that looks like this. Okay, so this is a good example of taking a distribution and applying some transformation of it so you can model it better. Okay, so then all you have to do is just change your interpretation of the coefficients. All right, so don't worry about creating these plots if you haven't, but do this part, okay? What we're going to do now is we're going to move from this model to say, rather than predicting their actual wage, we're going to categorize them into high wage and low wage categories, okay? So I'm going to say the high wage is if their hourly wage is greater than the mean, the overall mean of wages. Okay, so here's high wage, and I say if else hourly wage is greater than the mean of hourly wage, removing missing data. If that is true, then it's going to be 1. Otherwise, it's going to be 0. Okay, so then I say wages, select ID, hourly wage, and high wage. You don't have to do this part. This is just for the slides, but you can see for this ID, this person was not in the high wage category until they got to 8, and then they were in the high wage category. Okay? So now we can plot this, and I would do something like this. All right? So now I'm computing right here the mean for each category. Okay, so I'm grouping by high wage. So for the 0 group, what's the mean experience? And for the 1 group, what's the mean experience? Okay, then I'm going to use that within a plot. So here's I've added a bunch of transparency to this, but here's all of my people that are in the high wage category. And here's all my people that are in the low wage category. And you can see experience goes along the x-axis. So we have some people that have a lot of experience out here, but they're still in the low wage category. Similarly, we have some people that have 0 years experience, but nonetheless are in the high wage category. Okay, but on average, there is some separation between basically the probability of being in one of these two categories, right? So you would still, because you can see this blue star, or diamond rather, represents the average for the experience for that group. So you can see, if you just were to guess, you would say that generally people that have higher experience are going to be more likely to be in this category. Okay? So now we need to model this somehow. We could actually fit a linear model, right? This is what's known as a linear probability model. Okay? So here we say LM, we just have high wages as our outcome, and we put experience as our predictor, and wages is the data. Okay? When I display this, it's going to be interpreted linearly, so the probability goes up by 0.06 points for every 1 year of experience. All right? We can plot it, and it looks like this. Okay? So that looks okay, maybe, right? The problem is we're only looking at the data here for 10 years, which is actually, I think, the range of our data. But let's imagine for a second that we had somebody who had 25 years of experience, right? In that case, our model would predict that they would have a value of 1.5, which is impossible, right? That goes outside of the range of our data. Our data are bound 0 and 1. There's only two values, right? So as a general rule, the assumed data generating process should match the boundaries of your data. Okay, and that's the biggest critique of the linear probability model. Of course, you could truncate after the fact and say anything above 1, we're just going to say is 1. Anything below 0, we're just going to say is 0. Okay, and then from there on, everything is fine. This is still less than ideal from my perspective, but there are others that would strongly disagree with that. Okay, so here's 2 different blog posts about it. You can check those if you want. But this is legitimately very controversial with strong proponents on both sides. I tend to be more of the belief, and I'm not getting into arguments with anybody. You can do what you want. But I am generally of the belief that your data generating process should match the bounds of your data. It just makes more sense to me. Okay? So we can do that by using a different distribution. So instead of using a normal distribution, as we did before, we can use a binomial distribution. And this is what the binomial distribution looks like. We have n, so some number of draws from the binomial distribution, with probability p. Okay? So you can think of this in terms of coin flips, where n is the number of times we're flipping a coin, and p is the probability that it's going to be heads. So with a fair coin, p would be 0.5, right? So here's an example where we would do this through code, right? I'm using R binom, so draw data from a random binomial distribution where the n is equal to 10. So we're going to flip the coin 10 times. Size is equal to 1. So each time we flip it, we're only flipping 1 coin. And then the probability is 0.5. So here we go. There's our data. Okay. You can also, I get confused often when I'm doing this about n versus size. So I always have to look at the help documentation to remind myself. But when size equals 1, or n equals 1 in the equation form, that is equivalent to the Bernoulli distribution. Okay, so you will often see for binomial logistic regression, the outcome being assumed distributed by a Bernoulli distribution. And in that case, all your modeling is p, because n is 1 always. Okay. Another way you can do this, just as a side note, this is flipping them, right? So I'm saying one sample where I'm using 10 coins, how many heads do I get? Okay, so I got 5 in this case. So exactly 50%. All right. So this is the full binomial distribution. When we have size equal to 1 like this, which is going to be most of the time when, with the stuff that we're doing, then you have a Bernoulli distribution. okay? So what we do now is just like with our normal distribution, we embedded a linear model as basically a replacement for the mean in that distribution. We're going to do the same thing, but now we're going to embed that linear model as a predictor of P instead, the probability, okay? So the problem is, though, that probability is bounded, 0, 1, right? We shouldn't be able to go lower than 0, and we shouldn't be able to go above 1. So we need to ensure our model respects those bounds. And so this is how we do it. We do it through a link function, okay? So this is basically what this looks like. We have some generic function, f, which we're wrapping around p, okay? So now, rather than predicting this part of the model is still just a totally linear model, just like normal. There's nothing different about that at all, okay? The difference is we're doing it on some other scale that's not related to probability, but this function maps back to probability, okay? So it can map whatever scale we're on back to the probability scale, okay? So instead of modeling P directly, we model f of P, okay? And so the specific f, the specific function, is called the link function, okay? And this is just opens up a whole new world of possibilities. So link functions map the linear space, because this is linear, right? This is completely linear. It maps that linear space to the nonlinear space of probability, okay? Log and logit are probably the most common links. So when we're doing binomial logistic regression, we use a logit link. And so our model looks like this, okay? Again, instead of modeling P directly, we are modeling the logit of P, okay? The logit of P is actually defined this way, okay? Where P is still the probability, so it's P divided by 1 minus P, and then we take the log of that, okay? So this part inside of here is an odds ratio, okay? And because we take the log of that, we are now modeling the log odds rather than probability, okay? All of this, like I said, is not specific to multi-level logistic regression. This is just logistic regression generally, okay? So that means our overall model can be defined like this. The log odds are modeled by some linear combination of predictors, an intercept plus predictors, okay? What we actually probably want to interpret most of the time, though, is not log odds, right? Log odds is kind of weird and hard. So what we can do is we can transform that log odds back to probability using the inverse link. Okay, so this is how we do that. We take our linear combination of predictors, we exponentiate them, and we divide that by 1 plus the exponentiated version of our predictors. Okay, so this is the logistic function or the inverse logit. Okay. Both of those refer to this same thing. Questions on that? All right. It's basically just a sort of statistical trick to be able to embed a linear model as a predictor of P. And we use that link function so that that linear model gets transformed into a nonlinear space to map the bounds of our data. So here's an example of how we would fit a logistic regression model in R for just a standard single level version, okay? Instead of using LM like we've done in the past, we would use GLM, and then we have to specify the specific family, okay? So I'm saying family equals binomial, and you don't actually even have to specify the link because the link is a logit by default. but I like to do it just to make it really clear. We're using a binomial distribution, and we're using a logit link. Okay, so here's our output. We have an intercept of -1.65 and a coefficient for experience of 0.25. So how do we interpret this thing? Well, if we're thinking on the log odds scale, it's exactly the same as a linear model, right? So the log odds of a participant with 0 years experience of being in the high wage category is -1.65. For every 1 year of additional experience, the log odds of being in the high wage category increased by 0.25. Okay, so that's cool because we have this, right? So if this is 0, then the log odds of being in the high wage category are -1.65. And for every 1 year of increase in experience, the log odds increase by 0.25. Right? So that's cool. But outside of scientific audiences, and frankly, even within many scientific audiences, almost nobody's going to understand what that means. Okay? So we need to think about this slightly differently. All right. The other thing is that I've seen people do in the past is they will do things like just exponentiate this and interpret that. All right. That doesn't work. Okay. It might actually work in simple linear regression like this, but if you get into the multiple linear regression version, it doesn't work because you have to add the entire prediction together before you exponentiate. Okay. So you can't do that for individual coefficients. The other thing is, it is nonlinear, okay? So here it is on the log scale, all right? I'm saying, give me the predictions for someone between 0 and 25 years experience from our model, okay? And this is on the log odds scale, and you can see it is perfectly linear. That's what we would expect, right? We have a linear model of log odds. But if we look at this on the probability scale, we will see it is not linear. Okay, and the bounds go from 0, although it didn't go all the way down there, up to 1. Okay, and here it goes from 0 to, it can go to infinity. Doesn't matter, right? But obviously higher log odds are going to be associated with higher probability values. Okay, so if you're talking about log odds, you're talking about this line. But most of the time, you probably actually really want to be talking about probability because we have more intuitive understanding about that. Still not great, I don't think, honestly. But our model parameters are bound 0, 1, and it's nonlinear. So one of the things we can do that I always think is helpful, and I'll move through this fast, but is to make predictions by hand. Right? So this is how we map our log odds to probability. So let's, and these are our coefficients, -1.65 and 0.25. So let's go ahead and make a couple predictions, right? Let's look at our intercept. Okay, so this is the probability given experience is equal to 0. Okay, so then we would say -1.65 plus 0.25 times 0. That's going to give us -1.65. Then we exponentiate these things. That's going to give us 0.19 divided by 1.1.9. And that gives us 0.16. Okay, so there's going to be a 16% chance of somebody being in the high wage category with 0 years experience. What about for 5 years? We do the same thing. We're just going to multiply 0.25 by 5. We get -0.4. So that's going to be 0.67 divided by 1.67, and we get 0.4. So there's a 40% chance that somebody with 5 years experience is going to be in the high wage category. And for 15 years, it's going to be an 89% chance. Okay. So let's try to go back to our interpretation that we had before, but maybe make this in a way that more people might understand what it actually means. Okay. The first thing I would do is show the logistic curve. So that curve that I just showed you that is nonlinear, I would include that as a figure in my paper. In part, that's because I want to prevent people from interpreting this linearly, right? So it's not every year is going to increase, the probability is going to increase by this amount. The increase is going to depend on where you're at in those years, okay? So you can discuss probabilities at different x values, sort of how we just did, calculated at a couple different points, and then discuss those probabilities. And then there's also this divide by 4 rule, which only works for the coefficients. It doesn't work for the intercept, but it is a nice general rule. And what it is basically, if we're looking at that logistic curve, it is steepest when the probability is equal to 0.5, okay? So the slope of the slope, which is its derivative, is maximized at beta divided by 4, okay? So aside from the intercept, we can say that the change is no more than beta divided by 4. Okay, that's the maximum change. Okay, so for example, our coefficient is 0.25. So we divide that by 4, we get a value of 0.06. Okay, so we can say a 1-year increase in experience corresponds to, at most, a 6% increase in being in the high wage category. Okay. And that value is going to be, we could look at the actual curve and try to kind of find that value. So it's going to be probably, I don't know, somewhere around here. This curve is kind of weird because it doesn't go to 0. But basically the inflection point of that curve where it changes from going up to going down. Okay, that's where the curve is steepest, and that's the divide by 4 rule. Okay. Okay, so here's an example write-up. I won't read through it, but this is basically to say the same things I just said. Figure 1 referencing the divide by 4 rule, so 6% increase, and then 5, 10, and 15 years corresponded to these probabilities. Okay, that's one way that you can approach this so that hopefully a wider audience can understand these things. Okay, other distributions. So we're not going to talk about this a whole lot, but I just want to make you aware. So this is from McElrath. I think he's really good. But this is an example of different distributions that you can use depending on how what your outcome is like. Okay, so if you have a large mean, then a normal distribution is going to be great. Okay, if you have a smaller mean, and specifically it's truncated at 0, that's that gamma distribution that we saw very briefly. Okay, so basically if it has a lower bound of 0 and you have a smaller mean, then a gamma distribution might be preferable to a normal distribution because a normal distribution extends beyond 0. Okay, there's the exponential family of distributions too. And so that's like the Poisson distribution is one that's going to be best for count data. Okay, you can actually also use the binomial distribution for count data, specifically if you have a high mean. So if you have a low probability, then you're going to want to be more like a Poisson distribution. So that's when you're thinking about counts, like maybe you're counting birds or whatever, then your distribution is going to be really spiked right around 1 or 2. Right? Like most species you only see once or whatever. And then there's going to be some species that you see that like you see them all the time, like a robin, and it's everywhere, right? So then those are like, you see 32 of them or whatever. So that's going to be this really skewed distribution, doesn't extend beyond 0, but the like mean of the distribution is right down there at like 1.5 maybe, or something like that. Okay. In that case, you're going to want to use a Poisson distribution. And then binomial, I've already mentioned it for you know, a 0-1 situation. That's where we're going to mostly use it, but that's also referred to as a Bernoulli distribution. But you can use a binomial if you have high counts too. So maybe you're counting something where like the lowest count you would ever get is like 15 of them or something like that, and then you have an upper bound of like 50. Then a binomial would be a good option there. Okay. And we won't talk about most of those. We're really only going to focus mostly on binomial, but just so you're aware of these other ones. Okay? Questions on any of that? Okay, so now we have a basic review, hopefully, and maybe a little bit new look at what logistic regression is. So now we're going to talk about how do we take that and extend it to the multi-level perspective. Okay, so let's go ahead and do this. I would like you to read in this polls data. All right, so you're going to have to use Rio import probably because it's this DTA data type. And then you can do set class to Tibble DF, so it'll be a Tibble if you'd like. Otherwise, it'll be a standard data frame. Give you a minute to do that. All right. So this is polling data from the 1988 election. And this is from the Gelman and Hill book. It was collected 1 week before the election. It's a nationally representative sample. There are some other things that we would want to do with these data if we were actually trying to make inferences about it. We're going to ignore all of that for now. So baseline probability. Let's assume we wanted to estimate the probability that George Bush Sr. would be elected. Okay, so we could fit a single level model like this, right? How would we fit that model? Go ahead and write down or try to fit this model. Okay, this should look like this. Single level model, right? There's nothing beyond that. All we're estimating is just the intercept. Okay, so we're saying that the probability, whether Bush will be elected or not, we're assuming is generated from a binomial distribution where n equals 1. And so this is a Bernoulli distribution. And the probability is equal to p. And p is the thing we're trying to estimate, right? And then p is going to be the log of p divided by 1 minus p, which is equal to alpha, okay? So then we estimate it like this, right? GLM, general linear model, where Bush is predicted by an intercept, data's polls, family equals binomial, link equals logit, okay? So I can use display or summary on this, and we can see that the log odds of Bush being elected is 0.25. So there's, if that was 0, we would say that it was 50-50, right? So positive means that there's more than a 50% chance. So we can actually put this on the probability scale if we wanted to by doing something like this. 0.25 divided by 1 point plus exponentiate 0.25, you get 0.56. So we're saying overall, there's a 56% chance that Bush is going to be elected. Okay? But what if we wanted to estimate state level variability? Because obviously, if you know anything about American politics, there's a lot of between state variability in political election data. Okay? So if we want to do that, all we have to do is specify a distribution for the intercept variability. Okay, so we have an intercept that we've estimated. If we want to specify between state level variability, we just have to specify the distribution for that variability. Okay, so this is just going to be a normal distribution, just like normal. Okay, there's actually nothing different about this model from a standard linear regression model. It's just this parameter is now going to vary between states. And we're going to still assume that that parameter variability is generated from a normal distribution with some mean and some unknown variance. Okay? So how do we actually do this? Well, yeah, okay, before we get to that, what do you think this variability is actually going to represent? It's variance in this thing, right? But what is that thing?
variation in log odds scale?
Yes, it's the log odds, right? So this is the log odds, and this is between state variability in the log odds. Okay? Variance in the log odds. Okay, so when we're going to fit the model now with LME4, we're going to just swap Elmer for Glimmer. Okay? And then we also still have to specify the family and the link function, okay? Because Glimmer can fit other models besides binomial. So that's going to look like this. Go ahead and give that a try. We're going to load LME4. We're going to say Bush 0, 1s, right? It's predicted by an intercept plus intercept variability between states. Okay? The data is poles and the family is binomial with a logit link. Okay? When we call summary or display on M0, it looks like this. So here's our baseline log odds. It actually hasn't changed from before. Okay? But now we've also modeled the standard deviation, so the variance in those log odds between states. And as I said, there's a lot of between state variability here. And in this case, the variability is actually larger than the fixed effect itself. Okay, which makes sense to me because, as I said, 0 is going to be that 50-50 point. And so you're going to have some states that are strongly not voting for Bush and other states that are strongly yes voting for Bush. Okay. So the average log odds of supporting Bush is 0.25. That average varied between states with a standard deviation of 0.34. Okay. We can look at the state level variation a bunch of different ways. I tend to like to plot things, right? I just like to look at them visually. So for our states, I think there is a way that we can get the actual state names in here, but I didn't want to deal with it. So we don't know which state is which. We just have this like integer denoting the specific state, okay? But here I'm going to use broom.mixed to extract the random values from this, okay? So M0 effect equals rand_vals, and then I get this, okay? So this is random variation around that fixed effect, okay? I'm going to create a fancy plot here. It doesn't have to be this fancy. I don't know why, I just always have a hard time not making things fancy. But so here's my M0, right? I'm going to mutate, so the level being this thing, right? The state index is going to be reordered according to the estimate, so low to high, okay? Then I'm going to put estimate on the x-axis, level on the y-axis, so the state is going to be a categorical on the y-axis. I'm going to put geom error bar h, so horizontal error bars, layer some points on there, and then put a vertical line at 0, and that's basically it. The rest of this is sort of color stuff and whatever. And so we end up with something that looks like this, okay? Notice I've used a color scale here that corresponds to political affiliation. So we've got blue and red, right? So this is a strongly not Bush state, and this is a strongly Bush state, okay? And this is the probability for each of these, and then, of course, the standard error along there. All right. Let's add some predictors to the model now. So we're going to extend it. Let's include age, female, and black as fixed effect. Okay, so age is the age of the person who was polled. Female is an indicator of whether they identified as female or not, and then black is a dummy code as indicating whether they identified as black or not. Okay. We also, though, probably want to center age, because we don't want the intercept to represent 0-year-old people, right? So we want our intercept to probably represent the average age of our sample participants, okay? So you go ahead and try first. I'll give you 3 minutes. Well, we only have 3 minutes left of class, I guess. Well, we have 5 minutes, but so which would you prefer? Give me thumbs up or thumbs down. Do you want the 3 minutes to do this, or do you want me to just show you? Thumbs down if you want me to show you, thumbs up if you want to do it.
I don't think we have a thumbs down, but I'm
Okay, well, we got almost nobody responded. You don't have a thumbs down. Okay, so whatevs. I'll just show you. Okay, so this is how I would do it. Poles mutate age C is age minus the mean of age, right? And then we're just going to add those predictors to the model. And then I'm still only using state level variation. So now we have these fixed effects, and we can see our between state variability is actually increased. Okay. If we want to varying slopes. So this is the average slope, right? But if we wanted to know what the probability is for people who identify as black or who were coded black anyway, we could do something like this. So this is a probability where age equals 0, female equals 0, and black equals 1, right? So here's all the coefficients. We're going to multiply this one by 0, multiply this one by 0, and multiply this one by 1. And then we add them together, and we get 0.24 divided by 1.24. So the odds of a person who was the average age, who was not female, and who was coded black is 19%. Okay, so there's only a 19% chance on average that somebody coded black who was not female and who was the average age would support Bush. Okay, the other thing we can do is we can say that's the average for people coded black, but maybe we want to know the between state variability in that as well. Okay, so in that case, we just model that as a random effect as well. Okay, so this is all the same sort of stuff that we've done before. Okay, it's just the only thing that has changed is we have this binomial model rather than a Gaussian or normal model. And then we have this logit link that we have to deal with too. So we have to think about it in terms of log odds, and then we're going to have to transform that to probability to make more sense of it. Okay. One last thing I want to show you. This says I did this wrong. I mean, I didn't do it wrong, but I made it more complicated than it should have been, because I extract the random vowels here, and I was just realizing as I was getting to this point, I could have just asked it to extract something different. I can't remember the exact one, but instead I added the fixed effects to it. Okay, so there's another thing that you can request it to add, rand pars, I think, maybe, I can't remember, but that'll just add the fixed effects to it. We talked about that way back when. Instead, I did it sort of by hand here, but the point is, by doing this, we can end up with a plot that looks like this now. So here is every state, right? And this is the baseline probability of non-black respondents supporting Bush. And then the green dots is the probability of respondents who are coded black in that state supporting Bush. And so you can see overall, for respondents who were coded as black, the probability is less. And that's true for every single state, which is pretty revealing, I think. But then for some states like this one, right, the difference between non-black respondents and black respondents was small. Whereas like this one, I mean, like, or this one, it's like they couldn't really be much more different, right? So that's fairly interesting. And what I think would be even more interesting is you could also then include predictors of this variance, right? To see why in some states the difference between non-black and black people is very small, and in other states it's very big, right? And you could probably look at a whole bunch of different policies and things that would predict that. So this is on the log odds scale. If we wanted to put it on the probability scale, we could just do this, and then we get it like this. So this is the exact same thing, but now notice we're on probability scale 0 to 1. Okay, so that's it. For Bayes, you can refit it like this, and notice everything is going to be the exact same. You still use just BRM, okay? And then for the family, you will have to say Bernoulli instead of binomial, and then it'll go, and you'll have things like this. Okay, so I have a lot of slides in here, some of which we got through really quick. Here's PP check using bars and stat, so those are different versions. But I think we mostly got through it all. Some of it is quick. If there's specific parts of these slides that you want me to revisit next time, maybe email me and I'll make sure that we get through those parts and go through them maybe a little bit slower. But I wanted to make sure that we finished up on Bayes and that we got through this binomial stuff because that's the most important part for your homework, which is due next week. Okay, and that's just to fit a model, one model that answers a research question. Okay. So next time we'll probably talk a little bit more about Bayes for binomial logistic regression. I want to talk about plotting Bayes models more. Okay, and then we'll talk about missing data and piecewise growth models. That's my current plan for next week. Okay. We're 1 minute over, but does anybody have any questions or anything you want to check in on? All right. That's it then. I will see you next week. Please get in touch with me if you have any questions on anything.